Yeah, so today I'll be talking about sort of perspective on hydrodynamics as a kind of superfluid EFT for strong to weak spontaneous symmetry breaking, which is a sort of notion that I'll introduce uh, as we go through the talk. So let me acknowledge my collaborators. This is work done with my current PhD student, Xiaoyang, and my former PhD student, Marvin, who's now a postdoc at Chicago, uh, and also work with my current postdoc, Jian Hao. Uh, so first, let me just sort of say a few words about hydrodynamics more broadly. So I would say from a modern point of view, hydrodynamics is an EFT that describes and thermalization in chaotic many-body systems. It's a classical effective field theory, whether or not the underlying dynamics are quantum mechanical, but it's a sort of stochastic effective field theory. Okay. And the sort of historical paradigm for this is usually attributed to Landau. Landau maybe approached this EFT not quite in the way that one would like to from a modern perspective, but the way that Landau approached this EFT was as follows. So let's suppose that we're trying to study a minimal model of hydrodynamics. We have a single conserved charge, i.e. a single sort of U1 global symmetry. And because physics is local in space, so the conserved particles can't just teleport, across the sample. We write down a continuity equation for the local density of this conserved charge that I'm labeling as n. This is our single sort of equation of motion for the theory. And then, because n is the only slow degree of freedom, that's essentially the postulate that goes into this EFT. We need to write an expression for the charge current in terms of the density operator n itself. And this is called a constitutive relation. And what Landau says is that we should write down the most general expression that we can think of, compatible with all of the symmetries in the system and the second law of thermodynamics. And for this theory of a single conserved U1 charge, just let's say we have rotational symmetry. The simplest thing we can write down for this current is Fick's law of diffusion here in black. And then we can write down higher derivative corrections in powers of a sort of small parameter, which is the mean free path times the sort of inverse length scale in which we're studying the system. Okay. And so this is sort of at the equation of motion level. It has, the hallmarks of many of our modern EFTs. Okay, we have a small parameter. The regime of validity is long, time, and length scales. The one thing which is maybe a little bit different about this EFT than what we often teach in the sort of first semester of QFT is that this is a dissipative effective field theory. So if we look at the diffusion equation, which is what we get from plugging this equation into this one, we find that the quasi-normal modes have an imaginary part. Okay. Now, that's, well, it is what it is. It's an important part of nature. But it does make trying to sort of build a systematic effective field theory for hydrodynamics just a little more complicated than what we're used to. Because from a modern perspective, we usually like to build effective field theories starting from a Lagrangian and a list of symmetries to impose. But our theory for diffusion has to be dissipative, as we've just discussed. So we have to be a little bit careful with how to introduce this in a Lagrangian formalism, especially if we want to be quite careful about sort of listing all of the symmetries properly. And I would say that, at least in my opinion, this was sort of not done fully carefully until about 10 years ago now. There were a series of sort of independent groups that aimed to build a sort of genuine Lagrangian effective field theory for hydrodynamics. I think the cleanest construction of them was the sort of MIT group with Honglu and his students Crossley and Glorioso, and I'll be sort of summarizing their construction. So they said that to handle dissipation, so in the spirit of what's called the Schwinger-Keldysh path integral for a mixed state, which we'll be talking about more shortly, we have not one but 2 degrees of freedom for this effective field theory. And I'm going to label them as phi r and phi a. For the moment, you can think that phi a will represent sort of stochastic noise in the system, and phi r should represent the sort of observable density, or as we'll see, really, its time derivative. And they gave us a list of symmetries that we should incorporate into a hydrodynamic EFT. The most important ones are listed here. So firstly, we have time reversal symmetry, or in this kind of dissipative thermal context, usually called KMS invariance. You can think of this as an incorporation of the detailed balance condition. And what it says is that when we implement the time reversal transformation, this noise field phi a gets a sort of non-trivial shift. Okay, and that's going to be a very important feature that we'll discuss its implications sort of in a moment and then later on as well. Now, the second symmetry has to do with the U1 symmetries in the system. Actually, you could maybe say there are sort of 2 fields. Each of them you might want to think of as kind of like a phase field. And we think that when we have a sort of U1 invariant theory and we're talking about degrees of freedom as phases, it would make sense to sort of have this kind of nonlinear shift symmetry. But let me emphasize that only one of the shift symmetries is sort of just shift symmetry by a constant. So this noise field indeed just shifts by a constant, but the other phase field, this phi r, actually gets to shift by any sort of space-dependent function. And they gave some kind of heuristic argument for this that I don't want to sort of spend too much time on because I'll try to give you a better argument later on. But I think it's sort of fair to say that this was a little bit of a mystery in their original construction. And as I'll show you in a moment, it's sort of clear that it has to be there, but its physical origin is perhaps slightly unclear. Okay. Anyhow, let's take these symmetries and write down the sort of minimal Lagrangian up to irrelevant corrections that is compatible with all of these symmetries. And I want to just assume time reversal symmetry. It's a dissipative system, but this is fine. I have microscopic time reversal is consistent with sort of macroscopic diffusion in the presence of noise. This is the minimal Lagrangian that I can write down. And notice that this is complex valued. So this factor of I here is sort of encoding the fluctuation dissipation theorem. I won't sort of have too much time to go into that. But if we vary this Lagrangian with respect to phi a, we find the diffusion equation for dt phi r. So as advertised, somehow the symmetries that we've encoded in this theory are indeed enough to get us the diffusion equation. We didn't have to put in the diffusion equation by hand multiplying a Lagrange multiplier. That's, I think, what the sort of Martin, Sigia, and Rose sort of crew did in the 70s. Now I claim this is really coming from symmetries. Yeah.
So, can you give the instruction how the time reversal transformation have the form that you gave us?
Maybe. Okay. So a very quick answer is that in the Schwinger-Keldysh perspective, it comes from sort of flipping the 2 contours in the SK path integral. I'll give you a sort of maybe a slightly more whimsical derivation of something similar later on. But yeah. Okay.
Sorry, just so I don't get lost. So is there somewhere like this velocity fields here, or how should I think about this?
So
From
there's
this
no
perspective,
velocity fields here. This is not a theory that necessarily has any conserved momentum. So it is the minimal hydrodynamic theory. It's purely diffusion.
Okay, that's
But I think that everything I'm going to say would sort of transparently generalize to more conventional Navier-Stokes equations, just with a lot more pain in the process. So,
okay. Thank you.
okay.
Possible for it to be even without a U1 symmetry?
Well, you need some kind of
Only-
continuous symmetry to
Yeah, but there's
have.
only energy conservation, for example.
You could do that as well if you wanted.
Then
And
how
the
would
story
you
would
test-
be quite similar to what I'm describing here.
But this form has U1 conservation.
Yeah, this form is for U1.
So with energy conservation only, would that still be some phase, or what would be the degree of freedom?
So in Crossley et al. For energy conservation, it's actually this one's sort of slightly annoying, but roughly speaking, energy and momentum conservation are related to essentially like the analog of this phi field is like a mapping from the sort of cells of the fluid into physical space-time. So you can think of it as,
This is the Eulerian version.
Yeah.
Kind. So it's not represented here.
No, that's right. I mean, so here there's no energy and momentum, and the sort of coordinates are just the spatial coordinates. But conceptually, you can do something similar.
But
It's
there
just
is
more
energy
complicated.
conservation here, right? The time translation is energy conservation.
So I would think of this as like a kind of statistical space-time homogeneity, but not sort of think of it as like on average the noise is sort of time translation invariant, but individual instances of the dynamics break the symmetries.
I see. So this does not assume energy conservation.
That's right.
This Lagrangian.
Yes.
I see. Thanks.
I mean, do you have like some intuitive picture we should keep in mind for this system? Like,
For this Lagrangian, I mean, maybe not yet. The goal of the talk is to try to make this a little bit more transparent.
okay, thank you.
But I would say like one way you can think about it is you sort of needed some of this peculiar structure to get, like you need an odd number of time derivatives, relatively speaking, on one side of the equation versus the other. That's very non-trivial. And so the crucial thing here was this kind of KMS transformation that gave you phi A plus dt phi R with the I. Yeah.
The quantum field, what you normally call the quantum field.
Yes, phi A would be the quantum field.
Okay, thank you.
Yes. Okay. Right. So the question of this talk is sort of where do the symmetries of this Lagrangian, what do they really mean? Okay. Okay. So since hydrodynamics is a dissipative effective field theory, I want to argue that we should really sort of think carefully about what symmetries are in open systems. And what do I mean by an open system? Well, I'm studying quantum dynamics of mixed states rather than pure states. So density matrices rather than wave functions. And they can sort of be, of course, classical superpositions of pure states. Now, you might say that, well, I'm interested in studying a sort of closed quantum system, albeit at a finite energy density or finite charge density. Why should we sort of worry about open systems? And my perspective is that, whether or not the actual system is closed versus open, so long as the system that you're studying can't exchange conserved charge in our setting with the bath, it really doesn't matter. From the hydrodynamic EFT perspective, this EFT is going to be dissipative. And so we actually don't really care whether or not, the environment is somehow hitting you with dephasing noise or not. And in the spirit of generality, then, we should sort of consider symmetries in this more general open setting. And in this more general open setting, there are a few changes. The first one is that we don't really need unitarity in the dynamics. We just need the dynamics to be trace preserving. More interesting is perhaps when we start talking about symmetries. So if we have a pure state, we could say that this pure state is symmetric if some matrix U, which is a unitary representation of some element of our U1 group in this case, if when it acts on the state psi, it just rotates it by a phase or multiplies it by a phase. Now we ask, if we have a mixed state, what's the sort of analog of this? One possible choice would be to say that you multiply your mixed state rho by the same matrix U just on one side, and I want the same thing to happen. This is what I'm going to call a strong symmetry. But it's not the only valid choice. Another sort of intuitive notion of symmetry for a mixed state would be that I should really conjugate the mixed state rho by this unitary U. This is known as a weak symmetry. Okay. And any strong symmetry is weak, but the reverse is not true, as we'll see in some simple examples. Okay. The names are intuitive, hopefully. Okay. A simple example of the difference between strong and weak symmetries can be realized by a simple thermal state. So let me consider the following grand canonical state, unnormalized here and for the remainder of the talk, because quantum mechanics is linear, so normalization doesn't matter. So here is my grand canonical ensemble. It's not a strongly symmetric state because when I multiply by my sort of U1 operator on the left, I pick up a phase that depends on the charge of each state in the ensemble. And this ensemble has states with different charge, so it's not invariant. But this state is weakly symmetric if I conjugate by the total charge. Well, the total charge would just commute perhaps with this expression above, but you can also just explicitly see that the phases all cancel. On the other hand, the microcanonical ensemble is a state which is both strong and weakly symmetric. The microcanonical ensemble, where I sort of restrict the sum over states to a fixed charge sector, is strongly symmetric because if I multiply by the same phase factor on the left, I pick up the same phase for every state alpha. Okay. Hopefully sort of pretty easy. Okay. Now, statistical mechanics tells us that we should expect the physics is basically the same regardless of which of these two ensembles we work in. So in the thermodynamic limit, we should be able to do computations in either ensemble and get the same answer. And so I claim, or really a set of two very nice papers from earlier this year, claim that you should then think of a sort of thermal state, maybe more precisely the microcanonical ensemble, as exhibiting a kind of spontaneous symmetry breaking of the strong symmetry. And in the latter paper, they called this SWSSB, or strong to weak spontaneous symmetry breaking. Okay. So for the rest of the talk, the goal is basically to understand the sort of effective field theoretic implications of this strong to weak SSB in an open system. Any questions? This is a sort of reasonable point to pause. Okay. What the claim? The claim is that the microcanonical ensemble exhibits something called strong to weak spontaneous symmetry breaking. And I'll sort of define that a little bit more carefully later, but intuitively, you can think of having like a strong U1 and a weak U1 symmetry. We'd like to sort of understand a sense in which the strong U1 symmetry is spontaneously broken and what the implications of that are. And I'll sort of go into that more for the rest of the talk.
Yeah, will you mention how it's spontaneous symmetry breaking rather than explicit symmetry
Yes.
breaking? Okay, thank you.
Yeah. at the end, if you don't ask too many questions. If you do, then you'll never know. Okay. Yeah. So good. Okay. I should actually acknowledge there's been a number of sort of papers recently. Here are two of them that sort of have noted that there's a kind of broken strong symmetry and that this seems to be related to hydrodynamics. I'm hoping that my discussion will be very explicit about exactly sort of how this works. And I hope to convince you that SWSSB really explains everything about the structure of this Lagrangian, and it should no longer be mysterious where this comes from. Okay. In particular, the diffusion mode is essentially the Goldstone boson of strong to weak SSB. That's the sort of one sentence punchline of this talk. Okay. And it satisfies a sort of generalization of the Goldstone theorem to mixed quantum systems. Okay. And I might skip this point, but we can also sort of generalize this construction and talk about systems that I'll call non-thermal. That's a sort of very mild extension of these ideas. And yeah, if we have time, I'll explain why SWSSB should really be understood as spontaneous a bit later. Okay. Yeah.
Strong to weak symmetry breaking?
There is there is discrete SWSSB. That is something I'm not an expert in, but that was really the focus of these papers and much of the recent literature on this subject. So yeah, I will argue to you that the continuous case is actually much, much simpler for many reasons. But
Well, my question is whether in that case there is like a degeneracy or something associated to discrete strong to weak.
Sorry, what do you mean? Like,
Well, I mean, here, if you're assuming that there is a Goldstone for the strong to weak in the continuous case, then I would expect also degeneracy in the discrete.
I believe so, but I'm not 100% sure. I haven't thought that much about the discrete case, but yes. Yeah, okay. Good. So now I want to try to sort of spend some time convincing you that hydrodynamics really is. Yeah.
I've seen that there is no time evolution equation like a master equation. So my question is that is this just some steady state phase or
Sorry, I mean the question here is fundamentally about dynamics towards the steady state. It's not.
So it's not a steady state phase. It's just the focus on the state, not a.
Well, so okay, hydrodynamics describes the thermalization towards a specific steady state, but the effective field theory is the EFT of the dynamics sort of approaching, and if you will, fluctuations around this steady state. So.
Okay, thank you.
Okay. Right. So before we talk about hydro, I want to give you maybe a kind of eclectic perspective on EFTs for SSB in pure states using a slightly more kind of Hamiltonian formalism, which I think will be a little more transparent when we move to the sort of open setting. So let phi be our sort of phase field. N of x is the density of the associated charge. As you know, hopefully n and phi are canonical conjugate variables. So I can write down the following Lagrangian, n partial t phi minus some Hamiltonian dependent on n and phi. You can also, of course, think e to the plus or minus I phi are kind of our creation annihilation operators. The U1 symmetry of the theory is generated in the sort of sense of canonical transformations, is generated by the spatial integral of the density, requiring that this total charge has a vanishing Poisson bracket with h, requires that h doesn't depend on phi itself, only on gradients. Okay. Now, to say more, we should sort of specialize to the particular phase that we would like our effective field theory to be relevant for. If we're describing a superfluid phase, one kind of simple way we can think about the superfluid is that we would like it so that in a state psi, the state psi may be strongly symmetric, and I'll return to this point later. But yeah, even in a sort of strongly symmetric state psi, we expect that a superfluid exhibits long-range order, where if I sort of remove a charge at site y and add it at site x, this correlation function is non-zero, no matter how far apart x and y are. This means that this Hamiltonian needs to depend on gradients of phi. If it didn't, then there would be no energy penalty to configuration where, of course, these phases sort of rotated independently. So therefore, my sort of Hamiltonian is given by this expression. And notice that n essentially acts as a Lagrange multiplier. I can integrate it out, and I just get the sort of standard Lagrangian for a Goldstone boson of a U1. What if I wanted to study a normal fluid where this U1 is not spontaneously broken? What should I do in this case? Well, in this case, I should expect that this correlation function vanishes. If I kind of create a charge and then remove one very, very far away, I shouldn't care. Okay. So this correlator should vanish. And as a consequence, I sort of expect that I now can shift my phase field by a space-dependent function of x. Okay. This shift would not change this correlation function in the sort of long wavelength limit. So my effective field theory ought to have an enhanced shift symmetry, not under just constants, but under arbitrary space-dependent functions. And so now I would like to sort of claim that this mystery reparameterization that we had seen before is nothing but the sort of hallmark of an unbroken symmetry within our EFT. Okay. Now, just as a quick comment, why can we not add time dependence here? Well, remember that partial T phi is sort of chemical potential, which is conjugate to density, and this is a physical degree of freedom, even in a normal phase, so we can only ever add f of x. Okay. All right. Now we want to build the effective field theory for diffusion. And it's very tempting, given the story that I've just told, to say, well, I have a strong U1, I have a weak U1 symmetry, so the Lagrangian should really have sort of two n's and two phi's. I'll label the strong U1 Na and phi A, the weak U1 with R fields. And again, I'd like to write down some kind of Hamiltonian in quotes H, such that this is my Lagrangian. And now the question is, what symmetries should I impose? Well, from the discussion we've just had, we should expect that phi R associated to the weak U1 symmetry has a sort of reparameterization symmetry where I can shift phi by an arbitrary space-dependent function, while phi A only has a constant shift. And so in this sense, maybe we've explained the two most mysterious aspects, at least in my opinion, of the old hydrodynamic EFT. That's simply a consequence of this strong to weak SSB. Okay. However, let me try to spend a few minutes kind of quickly going through some of the other symmetries, like this KMS transformation that I had glossed over before. Let me try to explain to you where these come from. Okay. So firstly, we're talking about
excuse me, can you go back one slide? So is the second term NR time derivative of phi R is allowed it from the conservation of the density operator? Trace of density operator should be 1. So I thought the effective Lagrangian always at least one A field exists.
Yeah, I'll come to that point on the next slide.
Okay, thank you.
Yeah, good. Yes. So the first thing we have to worry about is that, right, our effective field theory needs to preserve the trace of the density matrix. Actually, okay, maybe I'll come to it in like 2 slides, but we'll get there. Yeah. So we can sort of think of this curly H as the kind of Lindbladian for the system up to a factor of I. And rho of T sort of needs to be positive at all times as a density matrix. So this puts, you know, even if we imagine that, okay, in this dissipative and noisy system, we're allowed to have a complex valued Lindbladian curly H, it needs to have a negative imaginary part. Okay, now let's talk about this trace preserving condition. So if we think, for example, about the density operator NR, what that's really doing is essentially conjugating the density matrix rho by the charge density operator like this. And this sort of gives us a commutator. So since the trace of a commutator vanishes, we can sort of freely add NR to the Hamiltonian, well, Hamiltonian in quotes. However, the strong U1 symmetry kind of acts as an anti-commutator. This does not preserve the trace. So actually for NA and NR, we're sort of not allowed to add NA on its own. You always need a copy of NR. And if this is sort of confusing because it's an R field, not an A field, I'll sort of, maybe I'll just say that we sort of struggled a bit on the notation here to use. But we think the one that we've used is the best. But in any case, there is sort of one copy of the field, which indeed is sort of not allowed to appear on its own, as in the sort of usual Schwinger-Keldysh formalism. Okay. Maybe just to say a little bit more about the notation here. So the 2 A fields are canonical conjugates, the 2 R fields are canonical conjugates. So this is sort of why they, yeah, anyway. Okay, I don't know. Maybe no one here will really be interested in this point, but to encode time reversal symmetry in an open system, there's a sort of natural way to do this based on trying to generalize detailed balance to quantum dynamics. And when you sort of go through the song and dance of implementing this transformation, it turns out that the NR and NA fields don't change. Phi R flips sign and phi A flips sign, but also gets an offset, which is related to essentially the sort of derivative of the logarithm of the steady state. This is a kind of thermodynamic relation, if you will. So mu hat is kind of like the effective chemical potential of this possibly non-thermal steady state that we're relaxing to. Okay. Yeah, so KMS is a subcase of, it's a subset of this for steady states that are beta H. Yeah. Okay, so now we can put everything together. The Lagrangian is this one, which we've seen before. Unbroken weak U1 symmetry gives us the mystery reparameterization. Spontaneously broken strong symmetry gives us just the sort of global constant shift. The trace preserving condition says that H can't depend on NA on its own. And time reversal symmetry gives us this KMS-like transformation. The most general effective field theory up to irrelevant corrections is now this one, where mu and mu hat are, well, let's say mu is an arbitrary function at the moment, and mu hat is sort of determined by the steady state. Okay. All right. For a thermal steady state, as I mentioned, so basically mu and mu hat are not arbitrary. They're related to each other because the Hamiltonian both generates time translation and also sets the statistical steady state. If we make this assumption, we can integrate out NR, which acts like a Lagrange multiplier. This tells us that basically NA and partial T phi R are related in this way. we write the Lagrangian in terms of only the phi fields, and now we've reproduced the sort of Crossley et al. Lagrangian from before, hopefully now with a clear understanding of every symmetry that underlies the EFT. Okay. Any questions? Yeah.
So you said that it's microcanonical ensemble which has both strong and weak
Yes.
symmetries, while the grand canonical has only weak.
Yes.
Right? So you are developing all this for microcanonical ensemble then, or how
That's
should I think
right.
about
So you can think of this EFT as really sort of our starting point is the microcanonical ensemble. But of course, the microcanonical and grand canonical ensembles give identical physical predictions. So,
But from the perspective of symmetries, it looked quite different, right?
for the grand canonical ensemble, I would say, it's a linear combination of many microcanonical ensembles, each of which has SW-SSB. So that's why the physics in the grand canonical ensemble will sort of be sensitive to the same spontaneous symmetry breaking.
Okay, thanks. Yeah.
Can you go back by maybe one slide earlier about like symmetry breaking pattern? Yes. So does it mean that you only break the strong symmetry, the strong U1 symmetry, and not the weak U1 symmetry?
Yes. So if you break the weak U1 symmetry spontaneously as well, then this gives you a superfluid, not the sort of normal fluid. That was a sort of also a part of the prescription that was known to Crossley et al.
I see.
Yeah.
And is there like any reason why you have to add two U1? Let's say we only have like one U1 symmetry in the system with one conservation law. Like, is there any way to say that, okay, we have to add one weak U1 and one strong U1? Like, is there any
No,
principle
the
for
point
that?
is basically that if you like, think of the microscopic dynamics as conserving just a single U1 symmetry. But now you sort of take this open system perspective, and you always get two U1s. If you can't exchange charge with the bath, you always have a strong and a weak U1 symmetry. So it's not optional. That's why the EFT sort of always involves two.
And may I ask as well, like, is the other way around possible? Like, can you break the weak U1 but unbreak the strong U1?
No.
Why?
So intuitively, okay, because the strong symmetry implies a weak symmetry. So I think on the slides earlier, if we just look at the definitions of strong versus weak symmetry, weak is always implied by strong.
Okay, thank you.
How do I generalize this to fluids without a conserved particle number?
Well, you want at least one continuous symmetry, and so you would, if for example you were talking about energy conservation,
You would just use that.
it would be a sort of similar story, but this phi would have a different physical interpretation. It would be more like a local clock, like the local time.
Sorry, which both
phi?
Both of them. You have two phis.
Yeah. So you would have again kind of two copies of like a local clock. You could think on each contour of the Schwinger-Keldysh path integral.
Okay.
Yeah. All right. Let me say a few words before the talk wraps up about the spontaneity, which was a good question asked earlier. In a pure state, for pure state spontaneous symmetry breaking, we usually diagnose it via long-range order. But we need to be a little bit careful here because we don't have a sort of a real notion of Hamiltonian for the mixed state case. So I want to give you a purely state-dependent way to diagnose SSB. For a pure state, the way I would do this is I would say the state itself had better be symmetric. For example, I lie in a specific charge sector in this U1 case. Therefore, acting with a raising operator on this state sends me to a different charge sector. All one-point functions of e to the I5 vanish. But two-point functions don't have to, right? I can remove a charge at y and create it at x, and get a non-zero expectation value. In other words, just to kind of restate this same thing, the two states where I remove a charge at x and I remove a charge at y are not orthogonal quantum states, even in the thermodynamic limit. It's a restatement mathematically of the correlation function. But that latter perspective actually does have a kind of neat generalization to open systems, where I can talk about the fidelity of two mixed states. Let me think of removing a charge on both sides of the density matrix at site x. That's going to be rho x. And I remove a charge sort of on both the left and the right at site y. And I can ask whether these two density matrices have a non-zero fidelity after I remove these charges far apart. If I give you an insulating state, the insulator will not have strong to weak SSB. If I remove a charge at site x and I remove a charge at site y, I get two orthogonal density matrices in this fidelity sense. But a thermal state does. I won't go through this calculation, but it's a short calculation that you can show that removing charges at site x and y gives you non-zero fidelity in the microcanonical ensemble. So this is my claim as to why we really genuinely do have spontaneous strong to weak breaking. And the last point I'd like to very briefly make is that this fidelity is completely unmeasurable in experiments. So, okay. Maybe how relevant it is sort of a question. But in this U1 case, when we have continuous strong to weak SSB, we actually can sort of relate, we can find a measurable local order parameter for SWSSB. And it's nothing other than the charge susceptibility of the theory. You can relate the non-vanishing of this to a non-zero charge susceptibility. I don't have time to go through that. But you can define this susceptibility in a way that sort of makes a very beautiful analogy to the conventional Goldstone theorem. Okay. So the susceptibility essentially is non-zero when a certain symmetric Green's function has a delta function at zero frequency. That delta function at zero frequency is saturated by the hydrodynamic diffusion mode if you look at finite frequency. And you can think of this as a kind of reason why you must have a gapless mode in this strong to weak SSB regime. And that gapless mode is precisely the diffusion mode. Okay. One thing which is different about SWSSB is that there's no Merman-Wagner theorem. So SWSSB exists in all dimensions. And this is just because we're not talking about thermal states of a Hamiltonian. Okay. All right, let me just sort of stop there. So I hope that I've convinced you that thermal states exhibit strong to weak SSB, and the effective field theory for that spontaneous symmetry breaking precisely reproduces hydrodynamics. This explains the symmetries of these hydrodynamic EFTs in a transparent way. And I think that there's a sort of interesting question of whether kind of driven quantum systems might also have some kind of new universality classes that we can describe. I'm not sure what the answer to this question is, but I think it would be very interesting to explore further. Thank you.
Do you know how the Goldstone counting would work? It's kind of funny because you're not changing the group. You're just going from strong to weak. So do you think it would always be one mode for any group, or is it only one mode for U1 and it's group dependent?
I haven't thought about that. So let me just.
Okay, that's fine.
Yeah.
Okay, thanks.
Yeah.
So the magnetic field is a diffusive mode in medium. And can one understand as also this kind of formulation?
Sorry, I didn't understand the first part of the
magnetic field is also diffusive mode in medium, and can one understand as a kind of energy mode?
Well, I would say from our perspective, sort of all all diffusive modes, as far as I can tell, sort of arise from this mechanism.
Or diffusive modes.
Yeah, I don't think there's a counterexample of it.
Okay, thank you.
So to follow up on my previous question, this charge susceptibility would just, if I had a fluid without particle number, it would just be thermal susceptibility?
Specific heat, yeah.
Perfect, okay.
So if you break time reversal symmetry, I would say very little would change if you have some kind of generalized time reversal symmetry like PT. So if you wanted to talk about like bias diffusion or like chiral anomaly, etc., I think this story will basically go through. If you want to sort of break time reversal symmetry without knowledge of the resulting steady state, then I kind of don't know how to systematically analyze that from this perspective. Yeah. So.
Hi. So normally with a Goldstone mode, if you were to explicitly break the symmetry, it will get gapped out. So is there some analog statement you can make here?
I believe there would be, yeah. So I think that explicitly breaking this strong symmetry would amount to sort of having some kind of fluctuation where the bath can sort of inject or remove particles from the system, and it drives you towards a sort of average density set by the value of the chemical potential in the grand canonical ensemble. And in this case, I would indeed expect there's a finite lifetime for charge relaxation, because you're ultimately not having to tell or like diffuse charge from one side of the system to another. What ends up happening to a charge fluctuation is it gets eaten by the bath. So